Buenas noches y bienvenidos. Voy a introducir Professor Vicky Caspy in English. So most of our time, Professor Caspy observes one of the densest leftovers of our universe. They are called neutron stars. The density is equivalent to when you squeeze 1.5 sun into the M40 around Madrid. For her work, she uses the biggest observatories on Earth as well as in space. Vicky studied physics at the McGill University in Montreal in Canada. She obtained her PhD in physics in the United States at the Princeton University in 1994. After that, she got a prestigious Hubble Fellowship, which she fulfilled at the renowned institutes Caltech and MIT. She became an assistant professor there at MIT in 1997 and joined the McGill University again in 1999. She became a full professor at McGill in 2006. Already early in her career, she became one of the top researchers in the world. Over the years, she has received about 35 awards and fellowships. During her scientific career, she appeared on average in 10 refereed scientific papers per year, of which about 15% she has been a first author. She is, however, not only a top researcher, she also easily attracts students and makes brilliant researchers out of them, like her. Moreover, she also reaches outwards and brings astronomy to our backyard, starting with her own family. I found on the internet a nice quote from her when she was doing high school. She said, "My ambition is to become famous and to be mother of 6 children." Well, she became famous, but she's only halfway her second ambition. I think she's one of the examples who successfully manages to combine astronomy with family life. So today, Vicky is going to tell us about one of the gifts of the cosmos close to her heart, neutron stars. Please enjoy.
Thank you. Thank you very much. It is a tremendous honor to be here and to get to tell you about my research and my work. I'm going to tell you about the cosmic gift of neutron stars. These are strange objects, these neutron stars. They amazed astronomers upon their discovery in 1967, and they continue to amaze us today. And I consider them a gift that keeps on giving. They could have been a scientific footnote in the annals of research, but today they are still studied by hundreds of astronomers worldwide, including here in Spain. And they continue to yield surprising and unexpected results in a wide variety of scientific subjects. And we can expect them to continue to provide us with new science gifts in the years to come, as I hope I'll convince you of in today's talk. Now this is, I'm talking about neutron stars, these strange objects called neutron stars, and you might wonder in the sky, can you see a neutron star? And here is a lovely image of a constellation you might be familiar with, the Orion constellation, where you can see many beautiful stars. And you might wonder which of these is a neutron star. And the answer is none of them is a neutron star. These are all regular stars like the sun. There's different types, different masses, different temperatures. But one of these stars that you see may well end up as being a neutron star. This bright red star over here called Betelgeuse, we think is a progenitor of a neutron star, and let me explain. That bright red star is a very large supergiant or a red giant star, a very massive star. And when massive stars end their lifetimes. That is, when they run out of the nuclear fuel that powers all stars and allows them to withstand the inward pull of gravity. Gravity likes to pull matter inward. Because of gravity, matter is attracted to it. Different pieces of matter are attracted to each other. So in all stars, we have a balance between nuclear reactions that keep the star from collapsing. But at the end of the life of a very massive star, like Betelgeuse, gravity wins because it's run out of nuclear fuel, and there is an implosion. The star collapses under its own weight. And that's what we're showing over here, an implosion of the core of this giant star. And what is sometimes left over after this implosion is a neutron star at the center. The star implodes, and at the same time, the outer layers of the star explode in a brilliant event called a supernova explosion. So we have an explosion and an implosion. And what's left behind is this object at the center, which is called a neutron star. If the star were much more massive than the one shown in this diagram, what would be left behind is a black hole. So neutron stars are very close cousins of black holes. They both result from the implosion of a massive star. The black holes are so massive that they collapse to a point, whereas neutron stars can still be held against collapse once they're formed. So what you're left with is a neutron star at the center and the remnants of the exploded star, what we call a supernova remnant on the outside, a gaseous expanding nebula. Let me show you, this is a diagram, let me show you an example. This is an image of the Crab Nebula, which is the remnant of a supernova explosion that was witnessed and recorded in many places on Earth in the year 1054 AD. And what you can see in this image are the filamentary remnants of the massive star that exploded. And near the center of this nebula, let's see, which one is it? These two stars here is the neutron star. The other stars are either foreground or background objects unrelated to the supernova. But one of those two stars is the neutron star. And how do we know it's a neutron star? We know it's a neutron star because neutron stars often, not always, but often have an amazing behavior. They can become pulsars. And what I mean by a pulsar is that they pulsate, so that if you looked at the center, this is a different image now of the Crab Nebula. If you look very closely at the center of the nebula, and you take photographs very, very rapidly. So in this case, this entire sequence of photos lasts only 33 thousandths of a second. What you see is that there's one star that is always on, that's always present. That is a boring, unrelated star, not in the supernova. But there's another star that turns on and turns off, and then turns on again and turns off. That is the neutron star. That is a pulsar. It is pulsating, it is turning off and on very, very rapidly. In this case, in the case of the Crab pulsar, the pulsar at the heart of the Crab supernova remnant, it pulsates 30 times every second. So if you could look at this with your eye, and it's actually very faint, you would have trouble seeing it, even with the big telescope, the flashes with your eye. You would just barely, and maybe not even, be able to make out the individual pulses. Now, why is it pulsating? What's making it pulsate? When I say pulsate, you might be picturing a star that's getting bigger and smaller, and that is not what we believe pulsars do. This is a schematic cartoon of a neutron star that is a pulsar, where it's rotating about some axis, which in this case is vertical, but out of its magnetic poles. So this is a magnetized star, very highly magnetized, in fact. The magnetic axis is in this direction, and out of the magnetic north and south poles, we believe there are beams of radiation, beams of light, that you see as a flash once each rotation. And so these objects, we can't see a picture like that. They're much too small and much too far away to be able to see this picture. What we observe is the intensity of light as observed at a telescope. We see it getting brighter and dimmer, so that when one of these beams crosses our line of sight, we see a pulse. That's what we believe the pulsing is. And from this movie alone, you can already know that there must be many pulsars in the galaxy that we can never detect from our position here on Earth. You would have to go to a planet somewhere else in the galaxy to be able to detect some of those pulsars. We see some fraction of pulsars in our galaxy. Now, I would like just to share with you some history about these objects, how they were discovered, because it's a very interesting story. They were discovered completely by accident. The existence of these objects was in fact predicted, but the way in which they are observed, the pulsations, was not predicted. And they were discovered quite by accident in 1967 at Cambridge University by a student, a PhD student named Jocelyn Bell. And that's a picture in 1967 of Jocelyn standing next to a telescope. And you might look at that picture and think, I don't see any telescope there. But in fact, there is a telescope. It's a radio telescope. This is a telescope that is sensitive to radio waves from the cosmos. And radio waves we detect from using antennas. And what this is, these are wooden posts with wires strung between them. The wires are acting like a giant antenna that detects the radio waves from outer space. And the intention of this telescope, it was built in order to detect radio waves from very distant galaxies, but they had no idea the major discovery that they were going to make once they built this telescope. Now, I say radio waves, and that might puzzle some of you. Radio waves, is that really a kind of light? And in fact, yes, it is. Of course, we are familiar with the colors of light that are in the rainbow. And here is, of course, if you break down regular white light using a prism, you get the different colors of the rainbow, from red all the way to violet. And of course, the study of optics was done by Sir Isaac Newton, who actually will appear again later in the talk in a very different context. But in fact, this light, the light that you can see with your eyes, is only a small part of a much broader spectrum. We call it the electromagnetic spectrum of light. There's many different types of light beyond the red. There's certainly the infrared, but even beyond infrared, and let me show you what I mean. This is the full electromagnetic spectrum of light, and you can see here the visual range, the range of the light that our eyes can see, is really a very narrow slice. In fact, light can exist at infrared. Infrared light exists at longer wavelengths. This is what's different about all these types of light is the wavelength of the light. So light is a wave, and the longer the wavelength, the redder the light in the visual band. But beyond visual, there's infrared, microwaves, and the radio band with ultra-high frequency, very high frequency, and the AM and FM radio bands. So all of this is the same kind of light, just with much longer wavelength. And on the other side of the visual band, there's the ultraviolet light, X-rays, and gamma rays, which you've probably heard of, and is another type of light. And so here are some common examples of the different types of light. The visible range, of course, you can see infrared is what the light that's given off by warm bodies. So all of you today are giving off infrared light. Radio, this is not an emitter of light. This is a radio reflector that can reflect light, radio light. X-rays, your hand does not give off X-rays. This is an image taken with X-rays that pass through everything but the bones in your hand. And this is a horrible explosion where gamma rays are produced. So just a few examples of different types of light. And so Jocelyn Bell was using her radio telescope when she noticed something very strange in the output of the telescope, something that she didn't expect. Now, this is a chart recorder paper. This is before we had computers. Before there were computers, people recorded the signals from radio telescopes using a device called a chart recorder, where there's this graph paper that had lines on it, and there was a needle attached to a pen that monitored the voltage of the currents flowing in the antennas that were receiving the radio waves from outer space. And you can see here that little scruff that you see, that line going across, that is the needle, that is the pen that's connected to the voltage of the radio telescope. And what she noticed is that this little blip over here, this is an actual reproduction of the paper. This little blip was unusual. She looked at that and she thought, that looks strange, even though this was something that she recognized to be interference, radio interference from terrestrial sources like radio waves or, of course, today, cell phones, something like that. In 1967, it was some radar or something like that. But she looked at that and she knew that that looked unusual. She was a remarkable student in many ways. Many students would have ignored this, but she didn't. And she went and went to the radio telescope when she thought this would happen again, and she turned up the speed of the chart recorder paper so the paper would flow out faster. And she could see what this little bit of scruff, this little bit of changing voltage looked like. And to her amazement, what she saw was a series of pulses. So in this chart recorder paper, the pulses happened to be going downward. It does not mean the telescope was sucking out radio waves from the sky. No, it was still, it's just inverted for uninteresting reasons. But what she saw was these regular pulses coming at, in this case, I think, every 1.19 seconds, very regularly. And this was unlike anything anybody had seen from the sky before. Stars don't pulsate. Stars don't go bing, 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 bing. This was a very strange thing. And she went to her PhD supervisor, Professor Anthony Hewish, who had been responsible for building this radio telescope, and she tried to convince him of the reality of these signals. And at first, it was very hard to believe, certainly for the professor, it was very hard to believe that these could be cosmic in origin. He felt they had to be terrestrial. But eventually, she was able to convince him that it was not cosmic, that it was cosmic in origin, and it had to do with their location and when they kept reappearing day after day. And they became very excited because they knew they had an amazing phenomenon. And at first, they believed that they were signals from an extraterrestrial civilization, from aliens. And so they called them little green men initially, because they thought that it had something so regular going off and on had to be a signal from aliens. But then she went back and poured through rooms full of chart recorder paper and found many of these objects on the sky very far apart, and it was clear it had to be a natural phenomenon. And then Anthony Hewish won the Nobel Prize for the discovery of pulsars in 1974. It's sometimes discussed, perhaps Jocelyn Bell should also have won the Nobel Prize, and some people feel that she was really denied that prize, but that is the sort of thing that gets debated for on and on. So today we observe pulsars, and what we see is the radio intensity from some position on the sky going up and down and up and down. This is not real data. This is a schematic diagram. We refer to the pulse period. The period of the pulsar is the time between successive pulses. In this case, you can see there's a little extra pulse. That's probably the other pole. We see one pole, and then we see the other pole. This is real data taken at a real radio telescope for an extremely bright pulsar. They're almost never this bright. This is unusually bright. Most of them, in fact, are very, very faint, and so we need to use today modern radio telescopes like this telescope in Green Bank, West Virginia, where, just so that you understand the scale, the diameter of this dish is 100 meters. So this is a building, and these are two buses over here. So this is a very, very large structure indeed. And we need that in order to detect the radio waves that are coming from very far away across the galaxy. Yes, so in this movie that I showed you before, this is, of course, very schematic. The pulsar, the neutron star, isn't really just a sphere with two cones coming out with some invisible magic going on here. There's complicated physics with messy currents and magnetic fields throughout this. A slightly more accurate diagram of a pulsar looks like this, where here is the central neutron star. Here is the rotation axis about which it's rotating, and here are the cones of radiation coming from the beam. And this large green structure that you see, that is called the magnetosphere of the pulsar. It is the region where the magnetic field is the most intense. And it's also a region that we believe fills up with plasma, with charged particles and gas. And I'm just pointing this out, this sort of donut-shaped region around the star, because you'll see it again later. And please understand that it's not really green. You can't really see it with your eyes. It's a region of intense magnetic field, and it could have been colored, purple or rainbow. It's just trying to show you the structure. Now, you might ask, in the Crab pulsar, it's rotating 30 times per second. How do these pulsars get to be rotating so fast? How do they achieve these huge rotational speeds? And the answer is that because they form in the collapse of a star, due to a basic physics principle called the conservation of angular momentum, even the small rotation of the massive star gets amplified in the collapse. So I have a movie here of a figure skater. And first, I apologize for the quality of the movie. It's a little pixelated here. But you will still be able to see what you need to see, which is that the figure skater, he will start out rotating with his arms spread way out, and even one leg spread out, and he will begin to spin. And then he pulls his arms inward and his leg inward, and you'll see him get very, very fast. This is a demonstration of the principle of conservation of angular momentum that applies to neutron stars as well. So there he goes. His arms and leg is out, and now he brings them in. And you see he brings them in, and he spins up very, very fast. There he is. And that's exactly what happens with a neutron star. That's why we think most of the neutron stars spin so rapidly. Now, let me tell you a few facts about neutron stars. The typical mass of a neutron star, the amount of matter that it has, is about 40% more than the sun. So about 1.4 times the mass of the sun. And if that's not a number that you feel comfortable with, perhaps think of about 500,000 Earth masses. So if you could take 500,000 Earths and then crush all of that matter into a radius of about 10 kilometers. That is what a neutron star is like. And so just to give you a feeling for the size of a neutron star, here is a map of the island of Montreal, where I'm from in Canada. And if you brought a neutron star to Earth, which I do not recommend, it's about the same size as my home, as the island, but with 500,000 Earth masses crushed into it. So that if you could go to a neutron star and take a teaspoon, it would be 1 billion tons or something like that. So this is not matter as we know it, and not matter we can simulate in laboratories. And as if that were not strange enough, they also rotate very rapidly. The Crab pulsar 30 times per second, but the fastest one that we know of actually rotates 716 times every second. So this is 1.4 times the mass of the sun, crushed into the size of a city, and rotating as fast as your blender in your kitchen. And actually, I was wondering how accurate that statement was, and perhaps there's been invented a faster blender. And so I did an internet search, and this, in fact, is the fastest blender that has ever been made. And it rotates, its maximum speed is 625 rotations per second. So pulsars, in fact, do beat the blenders, which is nice to know. Now, that fastest pulsar was actually discovered by my then graduate student, Jason Hessels, using this supercomputer. This was in 2006. And we need supercomputers because we collect lots of data from these big radio telescopes, and we subject it to very detailed analysis to look for repeating signals. And you might wonder, we continue to search for radio pulsars using the same techniques, but I want you to know that you can help search for radio pulsars as well. There's a program called Einstein at Home, where if you go to this website, you can download data from a radio telescope and put it on your laptop computer or your desktop computer, and it will automatically search for pulsars and send the information back to the organization. And in fact, Einstein at Home did find a pulsar in 2010, the first time the public has actually made a scientific discovery. Here are the discoverers. From Ames, Iowa, this very nice couple who gave their computer. But there's now today millions of people who are doing this, and you're welcome to do it also. The data that they searched, and which my research group is currently searching, are obtained at a radio telescope called the Arecibo Radio Telescope in Puerto Rico. It is the largest telescope in the world. This is the largest telescope of any kind in the world. The diameter here is 305 meters. So this is very, very large. And the distance between the bottom of the dish and the platform where the antenna sits. So the radio waves come down, bounce off the dish, and get recorded by an antenna inside the structure. This distance is about 137 meters. So it's a very large structure. It's used for a variety of astronomy, and I thought you might, this line here, that is a catwalk, that you can go and walk on that. It's a little wobbly, it's a little bit scary, but this is, visitors can go and can walk around on the structure. You can have perhaps 50 people up on there. It's a very large structure. The movie, it's used for a lot of astronomy, the telescope, is used for a lot of astronomy, but it's also used in movies. So you may have seen it in Contact, starring Jodie Foster. And here you see Jodie with the telescope in the back. And also in a James Bond movie, GoldenEye, with Pierce Brosnan. And here's Pierce Brosnan on the surface of Arecibo. And very interesting, Pierce Brosnan, the actor, refused to walk on this catwalk here. In the movie, it's a stunt double. And so I'm very proud to say that I have done something that James Bond was too afraid to do. Okay, now back to this very fast pulsar. When it was discovered, a famous professor from Harvard University wrote an article about it. And he titled his article, "A Neutron Star in F Sharp." And you might wonder, why F sharp? What did he mean by that? F sharp sounds like it's from music. And indeed, he meant it in a musical sense, because a pulsar that is rotating many hundreds of times per second is producing pulses that are the same as audio waves, the same as the sounds that we can hear. So we can listen to the sounds of pulsars by taking the output of the radio telescope and plugging it into an amplifier and into a speaker, the same way that you do radio waves from a radio station. And so I brought with me some sounds of pulsars that were recorded. The first two were recorded at radio telescopes. They're very interesting to listen to, partly because they really bring home how fast these things are rotating. But even you can hear some interesting astronomy. So this is a pulsar that is pulsating every 0.7 seconds. So what you're hearing every 0.7 seconds is a burst of radio waves. And you can hear sometimes a pulse is fainter than the next pulse. That's weather on the pulsars. But the pulses always come at the right time. Here is a faster pulsar, 89 milliseconds, that is rotating 11 times per second. And so here, if you listen carefully, sometimes pulses are totally missing. There's one that was missing. This is, again, this is the sort of weather in the pulsar that we actually don't understand the origin of. Now I'm going to play for you. This is the Crab pulsar, 30 times per second. And you're going to find that the signal now is annoying. And it's also so fast that your ear is going to have trouble. Some of you might not hear the individual pulses. This is actually a simulation of the Crab pulsar in a computer. The Crab pulsar is so faint that it's impossible to bring out the signal from the noise of the radio telescope. But you hear that the pulses are almost so close together that it sounds like a tone. And now when I play for you this very fast pulsar that rotates, this one is 1.5 milliseconds, or 642 times per second, you won't hear the pulses at all. It will sound like a musical note. So this is the music of one pulsar. For those of you who are familiar with music, this is not a pure tone. This has many harmonics because the wave is not a perfect sine wave. It's a narrow pulse, so it has harmonic structure. But still, it's nice to listen to. And in fact, I brought with me some other sounds of pulsars because in this one star cluster, this is a star cluster, a globular cluster called Terzan 5. In this one cluster, we know of 30 different pulsars, all very close to each other, so that when we point the radio telescope at it, we can hear simultaneously all of the different pulsars. And I'm going to play for you these different pulsars in succession so you can hear, and they're all very fast rotators, so each one sounds like a different musical note. And then together, you're going to hear the symphony of pulsars. So what we're doing is we're taking the signals of different pulsars and making each one louder so that you can hear the individual ones. when we really do observe it, they're all there at the same time. And once we get through each successive one, then you'll hear them all together as we hear them when we record data from this globular cluster. The other thing I should mention, of course, the notes might sound strange because they don't fall exactly at the intervals of music. They're at some random frequency. And there's your pulsar symphony. These pulsars were found by a colleague of mine, Scott Ransom, and there's a picture of him next to his car, and I thought this was funny because he put his pulsars on his license plate. Now, nearly all of the pulsars you just heard are actually very special pulsars. They are all binary pulsars. And what binary means is that all of these stars, all of these pulsars, are actually in orbit around another star. So we have the pulsar, and it's orbiting some other star, which can be a neutron star, or it could be some other star. So I would like to talk for a few minutes about binary pulsars. Now, pulsars are amazing because if you consider their pulses as ticks of a clock, those ticks are coming in extremely regularly. And if you used a pulsar as a clock, it would be much more precise than any watch in this room, even if there's a Rolex watch. In fact, the ticks of the pulsar are as precise as, at least as precise as the world's best atomic clocks. So for example, for this particular pulsar, on this day is a few years ago on some astronomers use modified Julian days. So this, I don't know exactly, perhaps it's November 21st, 1992, I could check. But it's not important. On that particular day, the period, that's the time between the different pulses, for this pulsar was exactly 0.00155780647, etc., where the last digit here is the uncertainty on the last number. This is one of the most precisely measured numbers in any area of science. These pulsars really are very, very good clocks. So I said they can be comparable to the world's best atomic clocks. And I say can be because not all pulsars are that good. Some are much less stable, but still stable to many decimal places. And also, we can't really say if they're better than an atomic clock, because that's the best reference we have. They're either as good or not quite as good or better than, and that's something, an active area of research we're trying to understand. But the point is that if you have this tremendously precise clock in a binary orbit, you can do amazingly precise studies of the dynamics of the binary. We can do this because of an effect called the Doppler effect, the Doppler shift. The Doppler shift is what causes the train whistle effect. If you're standing near train tracks and the train is approaching you, and if the conductor blows a whistle, you will hear the whistle change in pitch from where you're standing compared from when the train is moving towards you to when the train is moving away from you. So what you will hear is a higher pitch when it's approaching you, like this. So the pitch goes down. And this is because, just like in this diagram, here's a car. Here's a car traveling in this direction. If the driver makes a sound with the horn, an observer over here will see this wavelength slightly, the sound wave compressed a little bit because the car is moving in that direction, and it will be stretched according to an observer who's standing in the opposite direction. So the pitch, the wavelength or the frequency of the regular sound waves changes as it moves away or towards you. And of course, this Doppler shift is what allows police officers to detect when you're speeding in your car using a radar gun. They bounce a certain frequency off your car, and they see the reflection and how much the frequency of that radar pulse has changed. They can measure the speed of your car. So we do the same using binary pulsars. We have a near perfect clock orbiting another star. So it's sometimes moving away from us and sometimes moving toward us, and sometimes moving away from us and sometimes moving toward us. So that period, which is very precisely known, we can measure with exquisite precision that it changes during the orbit. The period seems to be longer when the pulsar is moving away and shorter when the pulsar is coming close to us. So you can see from the telescope, if it was light waves, you would see it look a little redder when the star is moving away from the telescope and look a little bluer. But this is the same effect on the pulsar period. The pulsar in a binary system shows a changing period, and it's very easy to measure because the pulse period is so precisely known. So here's an example. Here's the pulse period as a function of time for a pulsar that's in a binary. And these are real data points with the actual uncertainties shown. There's a huge effect, and you see in this case it's almost a perfect sine wave that indicates that the pulsar is in a very circular orbit around another star. Whereas here's another example. Again, the pulse period is plotted on this axis and time on this axis, and the data points with the measurement errors are shown here, and you can see in this case they describe the pulse period does a very strange thing, and that's because the pulsar is in a very eccentric, a very elliptical orbit. It moves much faster when it's near the companion than when it's far away. But the point is that we can measure these orbits with exquisite precision thanks to the pulsar clock. And so in 1974, there was a discovery. That was the year that the very first binary pulsar was discovered by Russell Hulse and Joe Taylor. Joe Taylor was the professor, and Russell Hulse was his student. Joe Taylor was also my PhD supervisor, so I know him very well. And they discovered pulsar, it goes by this name, 1913 plus 16. And here's a diagram of the orbit. Here's the pulsar and its orbit. And in this case, it was orbiting around another neutron star, although that neutron star, as far as we know, is not a pulsar. For some reason, we don't see it. And the orbit looks roughly like this. When the two stars are of comparable mass, they each orbit the center of the orbit, the center of mass. But what was really amazing about this binary pulsar is that the period of the orbit, the time it takes the pulsar to go around and come back to the same place, is only 8 hours. So compare that with, for example, the orbit of the Earth around the sun. That takes 1 year. That is a classical orbit that is not particularly fast. When you have two objects orbiting each other every 8 hours, we call such a system highly relativistic. And what do I mean by relativistic? I mean that the standard laws of Isaac Newton no longer work. You need general relativity, Einstein's theory of general relativity. So in classical dynamics, where the speeds in the orbits are relatively slow, like for the Earth or for objects in our solar system, Newton's laws, Sir Isaac Newton's laws, work perfectly well and are actually very simple to formulate. The simplest form, F equals ma, the force is the mass times the acceleration. But in a relativistic system, the speeds are so high, comparable to the speed of light, that you must use what we call general relativity, which is Einstein's theory, and is, of course, much more complicated to explain, but quite well understood. Now, when you have a binary pulsar that's really fast, here what is drawn is a grid, an imaginary grid. In general relativity, the motions of masses warp the fabric of space and time, so that instead of having a uniform flat space that is what we have in our intuition, the fabric of space and time itself is deformed and in a changing way, so that there are ripples produced, and these ripples caused by the motions of the masses in the binary, we call these gravitational waves. This is according to a prediction of Einstein's theory of general relativity. It's predicted these should occur. And as the masses give off these gravitational waves, that's releasing a certain type of energy. That energy has to come from somewhere. And so in general relativity, unlike in Newton's laws, we expect that the pulsar orbit should decay with time. That orbit should be shrinking with time. And that's something that should be measurable. And in fact, if we come back to the binary pulsar, the question that Joe Taylor asked was, is Einstein right? Do we really detect the shrinking of this orbit? Do gravitational waves really exist? And you could imagine, we should not believe in scientists, as gods. They produce theories that must be tested empirically. And in fact, in the binary pulsar, this is a very famous diagram. This is a measure of the size of the orbit versus years. And this was an experiment that took many, many years of observations to do. And you can see here in Newtonian classical dynamics, these data points from the orbit, and again, the uncertainties are indicated. These data, they're extremely well measured. They should have all lined up on this horizontal line. That's what should happen in Newtonian mechanics. But this line, which is a prediction, it is not a fit to these data. This is the prediction of general relativity. It beautifully goes through every single one of these points. This was a spectacular confirmation of general relativity in a regime where general relativity is a very strong effect. You might ask, but surely general relativity in Einstein's theory was tested before. And in fact, it was. While Einstein was alive, it was tested. But it was only tested within our solar system, where the speeds are all very small, and the effects of general relativity are just a small perturbation on the laws of classical mechanics. They're very, very tiny effects that require great precision to measure. You can see this is a huge effect. Yes, it took a few years to measure, but this is in a regime where you're testing general relativity in a much more significant way. And for that, Joe Taylor was awarded the Nobel Prize in Physics in 1993. Now, just the broader question that's quite interesting is general relativity right? General relativity is a cornerstone. It's the foundation on which much of our physical understanding of the universe is based, from the dynamics in binary systems in our own galaxy to the farthest reaches of the universe, to cosmology and our understanding of the universe itself. General relativity is extremely important, so it had better be tested well. And in fact, as we know, it passes what we call weak field tests in the solar system, where the effects are very small. It passes them with flying colors very, very easily. But in the strong field, so this is the weak field effect. Here is the effects around the Earth, for example, on a satellite. In principle, you can detect tiny deviations from classical mechanics, even around the Earth. But where it's really strong, like in this picture of what a black hole, for example, does to space-time, or this imaginary, an imagination from an artist of what a black hole does, where general relativity really matters, where it's a very strong effect, it is still not well tested. And there are alternative theories of gravity, many alternatives to general relativity that have been proposed. So let me tell you of another test of general relativity that we recently did that was really quite amazing. In 2004, there was an amazing pulsar binary system discovered, the double pulsar. In this case, the pulsar that was discovered is orbiting a second neutron star, but that second neutron star turns out to be another pulsar. It's the first example of this yet known. And the period of the orbit, the time it takes one pulsar to go around, is only 2.4 hours. This is the most relativistic system that we know of to date. And in a way, I like to call this binary system the pizza system, because you could not have ordered a more wonderful system for studying dynamics. You know, if you order a pizza, you order the peppers and mushrooms, whatever you like. If we could have, as astronomers, ordered the system, it is exactly what we would want. Highly relativistic, 2 pulsars to detect Doppler shifts from, and not only that, the binary orbit is almost exactly inclined relative to our line of sight, meaning that we view this orbit exactly edge on. The orbit is, you know, the binary orbit, it could have been in any orientation, but we view it exactly edge on, so that one pulsar actually eclipses the other pulsar for 30 seconds in every 2.4-hour orbit. So it has to be just aligned just right to get eclipses like that. And we are extremely lucky that this system did that. And so I'm going to show you an artist's conception of what that binary looks like during the eclipse, because we see an amazing thing. I hope you can see this. Here is the Earth. The distant pulsar is over here. This is not to scale. This is a zoomed-in view of that pulsar system, where you can see 2 different pulsars. One is much faster rotating than the other. One is a slow pulsar, and one is a fast pulsar. And this is how we see the orbit. You're going to see the slow pulsar here passes in front of the fast pulsar, and you can see the magnetospheres. They're not really blue, and they're not really visual. It's the region of closed magnetic of where we believe plasma sits in the magnetosphere. And it actually occults. It eclipses the radio pulsations from the fast pulsar for a brief period in every orbit. So you can see what's going on here. And what we were able to do is use this binary system in order to test another prediction of Einstein's theory of general relativity. So this double pulsar system turns out to be a wonderful laboratory for testing general relativity, because we can use the eclipses of pulsar A by pulsar B to study B's orientation in space, the direction that B's spin axis is pointing. In general relativity, it's predicted to change with time. It's an effect called geodetic precession. And what you see here, this is a diagram, real data showing the eclipse. So this is the intensity of pulsar A. You can see it's on, and then it disappears, and then it comes back on. But you could see these little spikes in the middle. And these little spikes are what allowed us to measure in detail the orientation of B's spin axis. And let me show you what I mean. And this is work that was done by my then student, René Breton, and you can see him there. So René made this movie where he's going to show, where we're going to see the, I think I have to click on it, see the, you're going to see pulsar B. You will see a big rainbow-colored magnetosphere. Again, it's not a rainbow. This is just a way of showing you the plasma region of the magnetosphere. And pulsar A, just as a dot, is shown. And what you can hear is the signal from pulsar A. It rotates about 5 times a second. About 50 times a second. And what you see is when it goes behind the magnetosphere of pulsar B, the pulses are eclipsed. And notice that at first, the pulses were eclipsed every half rotation of pulsar B, and then it changed to every rotation of pulsar B, just because of the orientation of pulsar B's spin axis and magnetosphere. So it's totally eclipsed, almost totally eclipsed now, and now it's about to re-emerge from behind. And this was all made possible by the fact that the orbit is just inclined just perfectly. Very, very fortunate, very lucky, happy circumstance. And the red now that you see, that's the actual data. Oops. The actual data, and the black was the model that we used to fit it. And so this is a very too complicated a slide, but just to tell you that with some complicated geometry and studying many, many of these eclipses over many years, we were able to test Einstein's theory of general relativity, which argued that some of the angles in the system should be constant, which they were, and some should be changing, which it was. And we were able to test geodetic precession in this very relativistic system. Now, one last point. I showed you this movie before, and I said that the motion of these masses is producing gravitational waves, which you can see as distortions in the space-time that's shown with this artificial green grid. So these gravitational waves, they are being produced by the pulsar. But another cosmic gift from neutron stars, not only do they produce gravitational waves when they are in binary systems, but we can also use pulsars to detect gravitational waves from other sources. So general relativity, it predicts the existence of gravitational waves. And Joe Taylor's binary pulsar demonstrated indirectly by measuring the shrinkage of the orbit of the pulsars, it demonstrated that gravitational waves exist. But there has never been a direct detection of gravitational waves as predicted should exist by Einstein. So if we could detect gravitational waves and study them, it would revolutionize astrophysics. It would take away the need for light from a very distant source. We could detect these gravitational waves in a totally different type of telescope. We could detect very distant objects that are dark, like black holes, but using a very different technique. One technique that has been suggested is this observatory called LIGO, which stands for the Laser Interferometric Gravitational Wave Observatory. And it's in the United States. And there are actually many other similar observatories in Europe and in Australia, and one planned for India, I believe. In this case, there's a very powerful laser that is split between one arm of this telescope, this observatory, and another arm. And at the end of this arm, which is about 4 kilometers long, is a mass hanging. And at the other end, there's another mass. And the light is sent down and then bounced back using a series of mirrors. And the interference pattern allows you to measure very slight changes in the distances of these arms. And a changing distance would be the signature of a passing gravitational wave. LIGO has not yet detected gravitational waves, and it's currently not operating because they are upgrading it to be more sensitive than it was. And we do hope it will detect gravitational waves in the near future. This is a proposed space interferometer, space telescope, called LISA, the Laser Interferometric Space Antenna, which, if it were to be built, would consist of 3 spacecraft, which each send out laser beams to the other, and these laser beams are used to measure very precisely the distances, in this case, 5 million kilometers between them. And this would be even more sensitive to gravitational waves. But that has not yet been built. But, as I said, neutron stars and pulsars, they are the gift that keeps giving. Pulsars are sources of gravitational waves when in binary systems, but pulsars can also be detectors of gravitational waves. We can build a detector of gravitational waves using pulsars, because just as pulsar signals are observed to be changing when they're in a binary system due to the Doppler effect, a passing gravitational wave will also create tiny changes in the pulse periods. And because they're such excellent clocks, and for this experiment, we only want the best pulsars. We cannot use any pulsar. It must only be the most precise clock. We can monitor those pulsars over many years, and if we have a large collection on the sky, we can look for changes that are correlated that will be the signature of gravitational waves that are passing. And the sorts of objects that we could detect this way are merging supermassive black holes. So just a brief word about these black holes. A supermassive black hole is a black hole that's 1 million to 1 billion times the mass of the sun. And we believe there is one of these in the center of every galaxy, including our own Milky Way galaxy. And so this is a galaxy called Centaurus A. This is a composite picture in the optical and the radio and the X-ray. And there's a supermassive black hole at the center that we think is spewing out these dramatic jets. This is an artist concept. The black hole you cannot see, not only because it's black and it doesn't produce light, but because it's obscured by some dust. But we believe in the existence partly in part due to the ejection of those huge jets from the center of the galaxy. But we believe there's supermassive black holes at the centers of every galaxy. And if you had two galaxies that are merging, that are colliding with each other, and we do observe this throughout the universe, those black holes will begin to orbit each other, and they will produce gravitational waves just like the binary pulsar produces gravitational waves. And so here is an example of a merging galaxy. These are two spiral galaxies that we believe are in the process of have just finished an initial collision, but are in the process of doing a spectacular dance around each other due to the mutual gravitational forces. It's called the mice because of these long tails of gas and stars that are produced in these types of mergers. And here is a computer simulation of merging galaxies, where you see two spiral galaxies come together, and as they pass through, the gravity distorts the galaxies very strongly and produces something that looks a lot like this particular merger. And then the two supermassive black holes will come together, and eventually they will merge. And so if we could look at this more closely, here is another simulation of two spiral galaxies colliding. Each has a supermassive black hole at the center. And if we zoom into those black holes, and again, we put this artificial grid, in this case, the distortions due to of space-time are enormous because these are 2 million or billion solar mass black holes. It produces a huge ripple in space-time, which we can then hope to observe back on Earth. Now, of course, this cartoon is bad because the galaxy is not beaming gravitational waves at the Earth. They are going everywhere in the universe. But in particular, they come, and if we observe a pulsar over here using a radio telescope on Earth, the pulses will seem sometimes stretched and sometimes squashed as the gravitational wave passes due to the distortion of space-time, so that the distance, you could think of it as the distance is slightly changing by the change in by the passing gravitational wave. So we are in the process of building what we call a pulsar timing array, in which radio telescopes all around the Earth are monitoring pulsar signals on a regular basis. And by combining all of these data, we could have the first direct detection of Einstein's predicted gravitational waves. And we hope that that will be the next neutron star gift. So to summarize, the title of the talk was The Cosmic Gifts of Neutron Stars. What were those cosmic gifts? Well, just the discovery in itself was really surprising and was a lovely gift from nature. Pulsar music you could think of as a beautiful gift, the symphony of pulsars that you heard earlier. Binary pulsars are, of course, a tremendous gift because they allow us to do sensitive tests of Einstein's theories and also to rule out alternative theories of gravity. And they have already allowed the indirect detection of gravitational waves. The double pulsar was a spectacular gift allowing a novel test of general relativity, and we hope soon to come will be direct detection of gravitational waves. And also possibly something we hope to find, the discovery of a pulsar black hole binary. We would love to be able to find something like that. We haven't yet, but that is on our list of things that we hope to do in searching for more pulsars. And so with that, I thank you. This is my research group, or a little older picture of my research group, and I want to thank all of my funding agencies for this research, and also, of course, thank the BBVA Foundation for inviting me to give this lecture. Thank you very much for your attention.